Hello, we're going to take a quick look at the periodic table and then we're going to watch a few other ed puzzles that'll really go through the mechanics of it, but I just want to go through a really brief reiteration of everything that's going on. Dmitry Mendeleev really looked at the different components of atoms, of different elements. He looked at like the density, what they look like, so their appearance, what was their atomic mass, because they could calculate that, and what were their melting points. And he tried to take all this menagerie of different information. He wrote them all on cards. Well, take a deck of cards and throw them down. It's not that easy to find anything. And as he studied them, he looked and he saw that there was really some patterns or some periodic things, like the days of the week. I always start with, some people start on Monday, some historically we start here Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. The next week is that it's periodic. And so he noticed that about every 8 elements that they seem to start repeating their patterns, and he based it on atomic mass. So what he did is, if, like, say I were to say find the one blue, you can find it pretty quickly. It's right here. But what if I wanted to say find one purple? Well, you'd have to hunt for it maybe a little more. It's down here. And if I put it into a repeating pattern, a period, it's much easier to find one purple or one green or 4 blue or 10 purple or 9 yellow. It it makes a difference when you arrange them according to trends. And that's what the periodic table is. It's really trends, and you'll see that coming up. Chemistry, remember, is really owes its origins to alchemists, people trying to create gold from lead. And they couldn't do it because unless you're able to do nuclear fission or nuclear fusion, you can't take one element and turn it into something else. But through alchemy, through this study of this desire to create gold, we learned a lot of properties of different chemicals, and it's the basis of it. And Mendeleev, here is his original periodic table, and he did it according to atomic mass. Later, and you'll learn another video who found that, we found out that you need to really go by atomic number, because there are a few in here that were backwards. The atomic mass increases before others. So atomic mass doesn't always increase the way atomic number does. But why Mendeleev was so prevalent and why we credit him for the birth of the periodic table is because he left gaps in here. But these gaps, he predicted the element that should be there. In fact, his predictions were so accurate that when one of the people found the element, they're like, no, it's wrong. The atomic mass is wrong. And Mendeleev basically went back to the guy and he said, retest it. He knew the element's properties so well by learning how the organization of that chart was, that he said, no, you have to go back. And in fact, the gentleman that discovered the actual element had measured its mass incorrectly. So Mendeleev was right. We have today slightly different organization of the periodic table. We go by atomic number. And you'll notice there's this little cut here because this group, family, they all have, these are highly explosive. We're going to watch a video on brainiacs about these. We can go all the way down to rubidium, cesium, and francium. It's not legal for anyone to have unless you're like military. 18 are all noble gases. So they line up on top of each other because they have similar characteristics. Everything on the left side of the table are metals. Everything on the right side are non-metals. And this little jagged line that goes through here, these are the metalloids. And there's only 2 things, right here and right here, purple, that are actually liquid at room temperature. Otherwise, everything else except for those 2 is a gas or a solid. So the reason why we break this out is because if we didn't, this is what the periodic table would look like. And I don't know about you, but that takes up an awful lot of wall space. And scientists understand that if we just drop this part down instead of having it here, we know it's supposed to be there. So that's why the lanthanides and the actinides are actually dropped down. Here's our periodic table. There's an interactive one. We've gone through this before because we've been using it. We have things like gallium. It was discovered in 1875 by a French chemist, and but anyway, it had properties that were predicted by Mendeleev for an unknown element, and it fit. They found it. They found the element that Mendeleev had predicted. And then we figured out in 1894 the noble gases, the argon, neon, krypton, xenon. Madame Curie found 2 elements. She was a Polish-born, naturalized French citizen, and her husband worked with her, and she is credited for figuring out the information on polonium, and radium. She named polonium after Poland, her home country. And by the way, she died of cancer because her whole lab is so radioactive that to this day, if you want to go into her lab or study her original journals, you have to sign a waiver because you are knowingly exposing yourself to radioactive material. It's still radioactive to this day. She actually kept some by her bed because it glowed. Francium in 1937, he predicted the properties of an element he'd called ectocesium. It was not discovered until 1939, sorry, by Percy, and she named hers francium after their country, France. And there's many more that have gone through. We've found many different things. In 1997, the International Union of Pure and Applied Chemists agreed to name the elements 101 to 109. Most of the names honor scientists like Lisa Meitner, sorry, it's been a long day, shown here in 1946. She, I believe, would have been a contemporary working on the Manhattan Project with our handy dandy Einstein. In fact, they really wanted her to work on the Manhattan project with Einstein, but on her tombstone it's written the thing that she had said, I will have nothing to do with a bomb. And so she should have been working on it, but she held up to her principles and did not work on that. We're going to go on to some more again. Here's our handy dandy periodic table. Remember, we like it better this way. It's just a little more compact and easy to see. Group 1, alkali metals. If I were you, I would take out that blank sheet of paper and start writing on it because you can use it on the test tomorrow. Alkali metals has 1 valence electrons. They're reactive violently with water. They're soft and shiny metals. So this is where you'd want to pause and copy this stuff down. Anyway, so but it's, lithium is highly reactive with air, so it has to be stored in oil. But potassium, as it's bonded with other things, we need it to survive, so you get a lot of potassium out of bananas. Lithium reacts with water, which is, interesting. So think about this. Sodium will also react with water and air. Lithium, it will react with water. Sodium is going to do more with water than air. It's slower to react. The faster it reacts. Lithium is not as reactive as sodium. Sodium is not as reactive as potassium. Potassium is not as reactive as iridium. So the explosions get bigger the farther down you go. But interestingly enough, remember, you take 1 explosive metal, sodium, 1 poisonous gas, chlorine, 1 is a metal, the sodium. The non-metal on the right side, chlorine, is a gas, and together they form table salt, and without it we kind of die. It helps regulate our body and our systems. We have a certain salinity that we have to have. So the next group 2, the alkaline earth metals, they have 2 valence electrons. Now remember, valence electrons, as we learned from, is the outermost shell of the electron shells. So everything that's full before it, and if that outer shell is full, it's a noble gas. If its outer shell is missing some, it's desperately trying to become full. So the rule of thumb is less than 4 wants to give them away, and more than 4 wants to pull in extras, because they are more determined to have an imbalance of charge, more electrons or less electrons than protons, but to have their outer shell be stable. And that's how we get chemical bonds to occur. So group 2 has 2 valence electrons. It's more reactive than most metals, except anything group 1 is way more reactive than group 2. They are hard and bright and white. They're good conductors of electricity. Big deal. 3 through 12, these are the transition metals. They're hard and shiny. They're good conductors of electricity. They're fairly stable. They're slow to react. We use these a lot in things like pigments in paint. Cadmium makes red, zinc gives you white, chromium is green, cobalt is blue. So we're going to skip over to 13. 13, interestingly enough, if you do 13 through 18, if you just knock off the 10, that tells you how many valence electrons. So there's actually 3 valence electrons in group 13. These are all metals with the exception of boron, which is a metalloid. And so right here, this is where we're starting to see that transition from solids to gases, and you have the metalloid family. It has kind of characteristics of a little bit of both. Again, make sure you're writing this down. 14, the carbon family, 4 valence electrons, 1 non-metal carbon, 2 metalloids, silicon and germanium, and 2 metals, tin and lead. I would not expect you to know how many metals, nonmetals, metalloids are in it, but I would expect if I gave you this picture for you to start to understand that the greens are nonmetals, these are my metalloids, the yellow, and the blue are my metals. That would be what I would expect you to know. Carbon is interesting with 4 valence electrons. Carbon chemistry is a entity unto itself because it can have 4 bonds, it can give them up, it can take them in. Carbon chemistry is something we are not going to really hit in 9th grade. You just need to know that it exists. OChem is a really interesting thing to do. Carbon is charcoal. Carbon is what makes us up. It's a really big deal. The nitrogen family. So have you noticed that was the carbon family? Now we're the nitrogen family. It's named after and up through, the first one. Although helium, it's not named the helium family. That's noble gases. So group 15, nitrogen family, has 5 valence electrons, 2 nonmetals, 2 metalloids, and 1 metal, bismuth. 16. The oxygen family has 6 valence electrons, 3 nonmetals, and 2 metalloids. There are no metals anymore in this family. We're getting close to the end of this. 17. Here's some handy dandy. The rubber tires contain sulfur. Some of the oxygen needed by frogs, remember, enters through their skin. Now here 17 is not named fluorine. It is actually called the halogens, like halogen lights, because these are the gases we're going to use there. There are 7 valence electrons. These are very reactive. Anything with 7 plus 1 equals 8. So think about this. Anything in group 1 is going to be really reactive with anything in group 17. Anything in group 2 really likes to react with anything in 16. That's a general rule of thumb. They can also react. 16 can react with 2 from group 1, so it's not a steadfast rule. It's just kind of a interesting tidbit. So the halogens, that 7 valence electrons, means they're very reactive. They only need 1 more electron to get to 8 to be stable. They are all nonmetals except astatine, which is a metalloid. And we've got fluorine contained compounds in toothpaste. Bromine is highly reactive and will burn skin on contact. You do not want to come into bromine gas. And the noble gases. These are the kings and queens of the element periodic table. They are the happy ones. They do not react. You can put a whole lot of electricity through neon and it'll glow, but it's not going to become something else. It's not going to change. It's not going to bond with something else because it's already happy. But it will give off some energy when you put more energy in. So 8 valence electrons, except helium, which obviously has 2, but since that only has 1 shell, that means its outermost shell is also full. These are very stable, very unreactive. They are colorless, odorless gases. But if you get down into, helium and neon, argon, krypton, xenon, and radon. Radon is a little radioactive, so, you got to be careful with that. And, granite in Minnesota, and that's our bedrock, and stuff scraped down into our glacial till, likes to decompose. So one of the byproducts of decomposing granite is radon. And so that's why you need to have your house tested. Almost everyone today, if you're getting a new house, will have a radon test to find out if you need to be doing that, because there's pockets. It depends on where it comes up. Your neighbors can be fine and you can be bad. Neon glows. It's really a nice, beautiful light if you can see it. The helium is the gas used to, fill a balloon. We don't use hydrogen anymore because, well, we all know what happened with the Hindenburg, and that's not a good thing. So here, semiconductors and metalloids, that's this right here. They have some of the properties of metals and some of the properties of nonmetals. That's why they're metalloids. They don't quite fit into either any of them. They are good conductors under certain conditions. And they use, but we use them a lot in electronics and computers because they kind of control when they work really well. Silicon chip we use in computers. Just as a quick, review, we talked a little bit about states of matter before. We're going to really get into that in the next unit. But take a quick look at this picture. And how many different states of matter can you see here? Think about that for a second. I see a gas bubble in the middle of that water bubble. So there's got to be some air there trapped in the bubble. And then you've got liquid, and then we've got the solid leaf. So don't we have 3 states of matter? We don't have plasma. By the way, that gas bubble is in the middle of that sphere of water. That would not happen really on Earth very well. This happened on the International Space Station, where you are in free fall, so you're experiencing zero gravity. The lanthanides. So now we're hitting this very top pull out, and they are soft, malleable, and shiny metals, and they are highly conductive. Last but not least, the actinides, mostly not found in nature. In other words, a lot of these are man-made. They don't stay stable very long. In fact, that because that nucleus wants to decompose, they're in fact very unstable. This is the other thing I wanted to show you. This is the trends, and we'll watch a video on this too, but you're going to notice that there are trends, there are periods. Remember, Mendeleev really saw this. And you are going to notice that as you go across from left to right, the atom size actually gets smaller. And as you go from top down all the way across, they all get bigger. So if you go from right to left on the bottom and very far left top down, the biggest elements is that cesium and francium. They have the biggest boom. They've got the biggest nucleus. They have a lot of neutrons, that means, to become bigger than something over here. So just remember that this is a trend, and it's very repeatable, predictable. So atomic radius, that is left to right, it gets smaller. Top to bottom, it gets bigger. A good test question. You need to say, yes, I've finished the notes. I hope you have watched the whole video, and then go on and watch the rest of the Edpuzzles that are going to go into a little deeper explanation on Mendeleev and trends and things like that than I did, and kind of the history of Mendeleev. So please pay attention to those. Anything you write down on a piece of paper, you can use on the test. So I hope you have a great day, and I will see you later.